us to recall. So the idea was to implement a subjective perspective in 4 artificial agents, and in particular compatible with some axioms of consciousness, which David stated briefly, but I won't go that much into it. So let's try to recall what we call an artificial agent. It's basically an agent with some beliefs about the world that it updates through, let's say, observations, and it acts, it planifies its action with respect to prediction of the consequences of its action on the world. So to do this, you need to introduce what's called the Markov decision process. In fact, a partially observable Markov decision process to talk about what is, let's say, an artificial agent with a model of the world and acting in such a way to optimize a certain cost. So you have a state space S of configurations here, and you're going to have a collection of actions, and actions are going to be simply functions, let's say stochastic, that sends a state of the set of configuration of the environment into another state. So for example, moving something, but it's stochastic, means that you have uncertainty on the, so you can, let's say there's randomness in the way you act. And you have a reward function, but for us, it's not that important. This is just to stipulate precisely what the Markov decision process is. And then, in fact, this is only, so when you have complete information on the configuration on the environment, which most of the time you don't have, so you have only access through observations. So when you have only access through observation to the state of the world, you still have a world model, let's say a state space S that accounts for all the possible states of your environment, or at least the way you model the environment, and then you have observations. And these observations are the information you get from sensors on the world. And you want to implement them as, you want to model them as simply a function that associates to a state times an action, we can forget it, just a state, so gives a certain observation. So for example, if I plan that I'm here, I know that I will see the piano. So if I'm here, I will see the piano in a certain way. This is the math that is here saying that Z associated to a certain state. An observation is the prediction of how states relate to observations. This is also stochastic. And most of the time, what you're interested in is the other way around. When I have an observation, what can I say about the state of the environment? Okay, so the aim here is to build a world model that incorporates perspectives on the world. And in particular, how, let's say, actions of the agent can relate to different perspectives on the world. So to do this, you're going to give a more refined notion of internal state space. So S, you're going to refine it a bit, and you will assume, so you're going to assume that a perspective taking is simply a group action on the space, and a world model becomes a space on which you can act. So a group or a G space, so just a space on which a group acts is just a function that's, so the actions now would be, parts of the actions will be internal actions, changes of perspective will be given by a group. And you have a map that tells you how actions change the state space, so the internal world model. And you assume some compatibility condition with the group, so basically respecting associativity. So that's the definition of the structure we put on the state space. And then if you want to go precising exactly the PO NDP setting I discussed before, so to get a model of agency, a model of an agent that has to plan its action, but it doesn't have a complete information about the environment, but it gets information only through observations. Assuming that the state space, so the space of the state of the environment has a group acting on it, the group corresponding to certain action of the agents, which are possible perspective taking on the environment, then you need to specify the way you go from once a transition. So the way you act, the way changes of perspective act in the state space, and just you have to include this kind of requirement, which means that some internal actions are in fact acting by the group, acting on the space. So this is nothing more than you have a pure MVP, and you assume that the state space inside is in fact has a group acting on it. But now if you do this, so here we assume that the group is the space is a projective group, which is projective space, which means that it's a set of lines in Rn. And if you assume this, it's a bit problematic because your observations are in R3, and the projective group 3D is not R3. because this is you cannot identify both. But what you can say is, in fact, up to, so R3 is an open subset of P3R, which when you close, it's a dense open subset. So basically, if you have a way to relate R3 to the internal world model, so observations R3 are the observations. So if you have a way in the Euclidean space to relate them to the internal world model, then you can play all the game we did before, where the internal world model is a projective space. So just take the case of the Euclidean space. I make an observation, I can relate it to my internal. So I'm looking for an object. The object is here. I think it's here. I see it with a certain certainty, and I can relate it to me thinking about where it should be. Now, if you do this with the projective space, you can't, because there's no way to identify R3 with P3. But in fact, there's no natural way. But if you assume a set of conditions, supplementary set of conditions, which if you give yourself a set of axioms, which means that locally around the position of the agent, you don't deform that much the geometry, and you assume that you have to be bounded. So the space in front of you has to be bounded. Then you have basically you have basically only up to a constant, you have one family of transformation that you can consider. So you can implement the previous model by feeding the inputs of the environment inside directly the state space of the agent, which is projective. So that's a very key important fact, to be able to use, let's say, the POMDPs with the PCM and then generate some behaviors for virtual agents, for example. So this gives this allowed to get several different simulations which are published, and David talked about it before. And so one thing that we're in particular interested in, David, didn't have time that much to go onto it, but I just wanted to make things precise, which I think is interesting. So what you have above here is just the POMDP with just one prediction at time t+1. So this is the internal world model, which is a projective space. This is your prediction of the observations. So the way that you relate the way you relate states inside of your model of the environment to observations. These are the group actions. So the way you chose a choice of an action allows you to, so the way the agent acts allows you to change your reference frame, and allows you to change perspective on your environment. So this I will explain just after why we can do this. And then here is just the same game, but at time t+1. So if I predict the consequence of my action, what will I get on the next state, and what will I get in particular on observations? So you feed the observation through the map that I just described before. So you have a choice of this map, but with the set of axioms basically only one, or let's say have a parameter lambda for these maps. And so you can feed the observation here and here. So you can forget about the environment and look only at this, where each space here is in fact the projective space, and play the usual game of POMDPs and try to solve, to find the optimal collection of actions with respect to a certain loss, which I will tell after. So what's important here is that, in fact, if you choose this map here, there's a natural way to translate transformations of this space of the agent, the way it moves, into changes of perspective. Because the reason is we're always centered on ourselves, but the way we feel about the environment, especially far away, is not Euclidean. So we want to find a way just to embed this, to put this inside of agents. So one task we were interested in is try to see what happens if you want to maximize, if you want to have an agent that has that's exploring its environment, looking for a point or several points. So be able to try, he's looking for several points, he doesn't know where they are, he's free to walk around a certain room. And he's going to get more and more information about where are the objects he's looking for. So you can define the notion of mutual information between so you have an a priori on where the object should be, and you're going to plan your action and see how it changes your a priori. And then because the way you relate your state space to observation, because this is fixed, so it corresponds to a small uncertainty around where the object should be, you're going to have, in fact, non-trivial mutual information between x1 and y, depending on the action you did. And in particular, it's non-trivial when you consider that the transformation here is projective transformation and not Euclidean transformation. So this is a theoretical result that you can show, is that if you choose the internal world model to have a Euclidean structure, you don't get the same behavior than when you choose a projective world model. Okay, this is just to go back on what people did, what the talks that we had before, and so this is the result. I just see it. I won't go into these details. So now I want to talk about pre-reflexive self-consciousness. So as Ken said, so the first part, which is things that I'm very bad at talking about, so Ken has said much better than me. So what my interpretation of PRSC is basically we want to find a way for the agent to be able to account for itself in the way it describes the environment. So it has a description of the environment, it has an algorithm that tells him how to behave, and we want him to be able to realize that, oh, in fact, I'm a special element of this environment. I have a way to talk about myself. I have a way to single out my own actions. So a way to do this would be, for example, if it has memory, it can keep track of its own actions. So by doing this, you can see that keeping track of your own actions and keeping trace of their consequences allows you in particular to distinguish your own actions from the changes that arise from other people acting in the environment. So that's a way to be able to account for your own presence in the way you model the environment. But we don't want to do this. We want to find a way to, let's say, find a minimalist way to talk about pre-reflexivity. And this, we do it in a static manner. And in fact, you can do it in several ways. And this is an interesting point, I think. So this is the work from Daniel Benquin and David and Kenneth, which is that if you exploit the dualities that you have on your space, you can have very weird effects that in fact seem to be related to PRSC, seem to think it resonates with PRSC. So the first duality you have is for projective geometry, so projective space, is you can exchange points and hyperplanes, and you can in fact, so you have a point inside of a line, inside of a plane, inside of the last succession of plane, if you're an MD. In fact, there's a way by duality to exchange the relation of being inside of a line being inside of a plane. And you do this simply by, in fact, if you look at how it works, so the projective space is the collection of lines. If you go to let's say spaces of 2-dimension, say if you take 2D planes in PNR, 3D planes, 3D vector spaces in Rn+1. And then what you can do is just take the orthogonal, so just what you would do in Euclidean space, but then it gives you something a bit interesting in the project, a bit more interesting, let's say, in the projective context. So I will try to illustrate it in 2D. So consider a point and look at all the points that all the lines that intersect, that contains this point. So you have a point and you look at all the lines that go through this point. That's called a pencil. The duality will tell you that the point will become a line, and all the line that contain your point become the points of this new line. So you have a line, you have a point, you have all the lines that intersect this, that go into this point. And you have a duality, which is simply using the orthogonal, like going back to the Euclidean space. So here E3, so we're going to R3. And just taking just looking at the orthonormal space to the hyperplanes, and this will give you a line, so it gives you a point. So you're going to have a way to identify a point to a line where each line that intersects, that passes through it becomes now a point. So a way to understand it is to say, for example, I see the object, I see all of you, you see me, right? So I see all of you, so your lines related to me, your lines that can trace a line towards me, okay, all of you. And then if I go in the dual setting, in fact, I become the line and you're the points. So that means that you, in fact, all the interactions I can have with one of you that is seeing me is in fact the same thing than just me, because you're just the points of my line. In 3D, it becomes a bit more complicated, and in D, a bit more complicated. But there's another example which I find interesting. So it's my way of formulating it. Ken has probably a better way of doing it. We were discussing about this yesterday. But now it's an analogy. You're thinking about something, so you have a thought, or imagine a perception. Okay, so you could say I belong to my thought. I'm a thought, but I have another thought, so I'm inside of my thought. Just an analogy. And then this duality, in some sense, here it doesn't exist, but just an idea, is to say, in fact, the thoughts now becomes the points of my plane of thoughts, so I'm conscious of all the thoughts that I have. So once I am in a relation with the thought, basically, if I apply a sort of duality, then in fact the space of all my thoughts is exactly who I am. So this is the kind of tricks we want you to play on. in particular to try to induce a kind of coincidence or a kind of ambiguity for the agent to be able to talk about itself. So another static way of this, another duality that we can apply and that we can use is the one of G space. So it's one where groups act on some spaces. So the simplest example of a G space is a homogeneous space, like the projective group, like the projective space, sorry. It means you take a point and you can go to any, let's say, other point through a group action. So the agent acts, okay, so you're in R3 or our projective space, and you can say in R3, you just translate. So any point is just, you choose a point and you go to any other point by translation. So here, translations are the actions of the agent. So if you do this, it means that if you choose a reference point, you can access all the other environment through your own actions. This is what we basically use when we think about the projective space as being a change of frame, actions of the agent being change of frame. It means that I can imagine myself anywhere in the environment. From there, I can reach everything. So that's the way that we think about the projective space as being potential. Each point is a potential action. But now you have something even more interesting, which is that if you, so this is very overthinking Yoneda lemma, right? I mean, especially in this context, but I will tell you why it's interesting, because if you go to more general setting, it's maybe a way to generalize the result. So here, in fact, we're just going to explain that any reference point is nothing more. So a choice of a reference point for the agent for which it can act and enact on all the environment is in fact in correspondence with all the points of the space. So this in the projective case is completely trivial. It means that you choose a point, you can reach everywhere, and any point of the any point of the, not even homogeneous space, the G space is in fact any choice of reference. So what I mean by choice of reference, it means that you remark that the projective space is simply a way to represent the way that you act in your environment. And if you do this, you can rebuild completely. Let's say the space in which you are. So okay, so it's a bit more precise than this, but so the idea. Oh, how can I explain it? So just one second. So anyway, so here the transformation, so you have transformations, you are just like the actions of the group. And you can rebuild completely the actions of the group, let's say, or at least you can, okay. If you choose a reference point, so if you choose a point from which you can, let's say, represent all the way you act, then any reference point is exactly the space that you're acting on. So this is this result. So this is very like, so basically this is just saying that any point is choosing a point that is inside of it. But what you're saying behind choosing a point that is inside of it is that there's always a possibility to enact on the environment from this point. And this is what I said here. So the statement here says that this is the same thing. So any way to represent the group acting on the space depends on the choice of a reference point. And the set of this reference point is exactly all the space. But as we said, the reference point is, so this is the point from which I represent my own actions on the environment. So it's the zero I take when I move, when I represent the environment. But this is the only trace that we have of the agent in the environment. So it means that now you can start saying, in fact, I can identify places in the environment with possibilities for the agent to account for its environment, for a way for him to frame its environment. So take a reference point and from there act. I'm not saying something more interesting, but I can start saying what I want to do, and maybe say something that I didn't put on the slides, but how to do it maybe some way. So until here, I didn't say much. I just said, okay, reference points corresponds to points in the space, but now I have beliefs on the points in the space, so I can rewire them because there's a bijection with reference points of the agent. That's what I wrote here. Most of the time, if you want to account inside of a generative model for the agent talking about itself, you need to put more parameters, which corresponds to the state of the agent, and it keeps beliefs about its own state by the way it acts. So you need to enforce it to act. You have to enforce the parameters of the agent inside of the module you have of the agent. But we don't want to do this. We want to find a way to exploit, let's say, this kind of ambiguity between the environment and the state of the agent. so that the agent can start talking about itself. So this is like so in an implicit way for the agent to talk about itself, it just identify a point with a reference point through the duality I was discussing just before. And so I have a distribution on X, so I have a distribution on couple, so I have a distribution on phi. You don't gain much. But because you don't gain much, because as an external modeler, you just see the agent doing a task, for example, exploration, and you cannot distinguish this task from it trying to explore something about itself. But in fact, you can gain something, and this is not in the slides, but which is that there are several different actions that keep the reference point the same. And so now having a distribution on all the points of the projective space and having a distribution on the reference points, there's an ambiguity because in fact, the reference point is a choice of neutral elements, so it's a choice of not moving. And if you look directly in the group, you have an ambiguity, which is all the actions that do not change your reference point. So you can still imagine if when you start updating your a priori, you do it in an approximate manner, you can still have an agent that is simply trying to explore a task, which is curiosity inside of its environment, and start thinking about, oh, maybe in fact, I have some transformation that do not change the way I reference the environment. And I can start to do tasks. So for example, exploration on this. So that's a way to, let's say, it's a way for the agent to, let's say, have an initial task and start doing something completely different. Just through the way it accounts for its environment through action. And so, yeah, I don't know how much time I have left. Maybe it's over. Okay, so yeah, what David was talking about multimodality before. So I can say that G-space are very limiting. Just I give one example, which is that if you do an observation, most of the time, what you're going to feel is if you have an instability because of your environment, then you're not going to stay in the same orbit of the action of the group. So you cannot use like homogeneous spaces or G-space to account for features that are very features like we see about the environment. So for example, an object representing an object, because it could change and then the action of the group on it wouldn't give you, it gives you an orbit, but it doesn't give you you have several orbits, so you don't have a homogeneous space anymore. The way to try to avoid this kind of instability is just looking at function over a space on which the group acts. And the space, so this is this function here. So a set of features, R for each element of X. And when you act on X, you in fact act on the features at the same time. And this, I won't say more. If you have questions, you can ask me. And thank you very much for your attention.